Good afternoon, everyone. Thank you for making the trek, the frigid trek to far eastern Siberia for our session on permafrost. It's really great to have you here to discuss a really important and rapidly changing component of the cryosphere. All right, permafrost is the frozen ground that underlies vast extents of the northern high latitudes, as we see here in this map. Our extent in the map is indicated by the colored region. So we have vast expanses across Eurasia, the mountainous region and the Tibetan Plateau, as well as across the northern high latitudes in Canada and Alaska. With climate warming, we're seeing rapid and extensive permafrost degradation. An example from Siberia here, interior Alaska here, far eastern Russia in this photo, and a coastline in Canada here. Permafrost thaw is driven by changes in precipitation, temperature, as well as disturbances, including wildfire. Thank you. The consequences, in addition to these dramatic landscape changes, include the release, the potential decomposition of frozen organic material or carbon that's been released from the frozen conditions where it's been held for millennia. The release of this permafrost carbon can change the atmospheric forcing, leading to further temperature rises, leading to additional permafrost thaw, enhanced microbial activity, and further greenhouse gas emissions, and what we call the permafrost carbon climate feedback. This is what we'll be talking about in our session here today. My name is Claire Treat. I'm a senior research scientist at the Alfred Wegener Institute for Polar and Marine Research in Potsdam, Germany. I'm joined here by Christopher Byrne at the far end, the president of the International Permafrost Association and the Chancellor's Professor at Carleton University in Ottawa, Canada. We have three panelists joining us today. We have Gustav Hugelius, Professor of Physical Geography and Vice Chair of the Bolin Center for Climate Research at Stockholm University. Emma Lathrop, an early career scientist and president of the Permafrost Young Researchers Network, and Guido Grossa, head of the Permafrost Research Section and professor of permafrost remote sensing at the University of Potsdam. So we'll start out today with short 5-minute statements from our panel members, followed by a facilitated panel discussion, and then we will open the floor for questions and discussions, particularly related to the policy recommendations that have been discussed earlier. All right, without further ado, Gustav, please.
Thank you very much, Claire. So I'm going to start by talking about really sort of big picture, overarching futures that we can expect from sort of thawing permafrost, and also related a little bit to what's presented in the last IPCC report, georisks. So you already saw a map of permafrost, and you can think of permafrost and as sort of a sleeping giant in the global climate system and in the global carbon cycle. The permafrost region is immense. It's about 17 million square kilometers, which is, I think, about 3 times the size of the European Union. And with every degree of global warming, we lose roughly 4 million square kilometers of permafrost. So we lose 1 EU of permafrost area over a long time with 1 degree of global warming. And then this is obviously a concern because of the very large amounts of carbon that is stored in the permafrost region. This bubble plot here shows the most relevant carbon pools in the Earth system or in the global carbon cycle. The size of the bubble is proportional to the size of the carbon pool. You see the atmosphere, almost 900 gigatons or petagrams of carbon, and then you see the biggest circle in the middle is the global soil carbon pool. That's the largest reactive pool in the global carbon cycle. And the orange circles are permafrost. So roughly half of the global soil carbon pool is made up of the global permafrost region. More than twice as much carbon in this region as in the atmosphere, or 3 times as much as all living vegetation on Earth. This means that even small disturbances to this carbon pool can have massive consequences for the atmospheric carbon pool and the global climate. So permafrost thaw is not always as dramatic as in this image. I still like it because it has the little person there in front that gives us sort of the dynamic. We have humanity in the front with this vast expanse of thawing permafrost in the background. This little person is actually sitting up there in the audience, who's in the image in this case. But of course we're concerned with the global, or with the permafrost carbon feedback, whereby global warming thaws permafrost. This happens everywhere in the permafrost landscape gradually from the top down. So what we call the active layer thaws every year, and it also happens more abruptly and rapidly, as in this image, from the side, or when ground ice disappears. And this leads to greenhouse gas release because organic matter that's been frozen, freeze-locked in the permafrost for thousands of years becomes available for microbes to decompose. And when they decompose that, as a side product of their respiration, they produce CO2 or methane. There's also a lot of direct impacts to ecosystems, infrastructure, and humans, and a multitude of other negative effects of permafrost thaw, which will be presented later on. So permafrost thaw is, in some areas it may be reversible, but a lot of permafrost thaw processes actually cause, at least at policy-relevant timescales, irreversible change. And this is largely because there's not only a lot of carbon in the permafrost, there's also a lot of ground ice, massive ground ice. In this case, you see some people pondering the upper corner of a massive ice wedge in the ground in Siberia. This ice wedge is about 10 meters wide and probably about 30 meters deep. So in an area like this, more than 50% of the volume of the ground is made up of pure ice. And when that melts, the land surface collapses. So you see this little graph shows over time how the ice wedge is degrading, and then the whole land surface changes. This causes surface collapse and complete reformation of the ecosystem or of the system. And these abrupt thaw landforms can and will emit a lot of CO2 and methane over long timescales after thaw, even if climate should stabilize. So if we think of this omnipresent gradual thaw that happens across the permafrost landscape and the abrupt thaw together, that adds up to really massive emissions of CO2 and methane. This graph shows you in CO2 equivalents, so here we've converted both methane and CO2, how much greenhouse gases we expect to come from the permafrost cumulatively by the end of this century. So how much will have been released by 2100 if we cap global warming at 1.5, 2, or 4 degrees. The black symbols shows what was estimated by the last IPCC report, which did a really good job in trying to summarize permafrost carbon emissions, because it's not yet included in the models that the IPCC uses. But they didn't include the effect of the abrupt thaw that would be added onto this. And then you have these purple bars showing us really massive projected emissions by the end of this century that might even match the complete remaining 1.5 degree carbon budget. Although those emissions happen at different time scales, because us humans will actually eat up the 1.5 degree budget in a matter of years. So, but still, even further emissions will then come from the permafrost. Another complication is overshoot warming. So if we overshoot our target temperature, the green line there takes us directly to the target temperature, which would be nice, but if we would overshoot it, we have the two complications. The first problem is that the permafrost will push the overshoot warming even higher because it has its own feedback. But the second problem, which is perhaps more urgent, is that actually the loss that happens of permafrost during the overshoot period, when we're in a warmer world before we go back down again, that will be largely irreversible. So if we account for overshoot effects, so if we go above 1.5 and then go back down with some negative emission technologies in the future, we get even higher projected emissions going into the future. You see this from purple to yellow to red with high overshoot. And also very concerning, and something that we really need to think about, is that these emissions are committed for several centuries. Even if we cap warming in this century, the permafrost is a slow component in the Earth system. It will keep emitting for centuries, which means that the damage we do now, we are effectively binding and committing several future generations to have to use negative emissions to balance the damage we're doing now, even if we cap at 1.5. So the damage we're doing is long-lasting, and we're really binding future generations to have to deal with the mess that we are creating. Thank you. I think that is what I wanted to do. So I'll hand the word over to Emma.
Thank you, Gustav and Claire. For policymakers, what is crucial to understand for mitigation and planning efforts is what the magnitude, timing, and form of permafrost carbon release will look like in a warmer world. Another way to word this is how much carbon will be lost, over what time frame, and in what form, in greenhouse gases, carbon dioxide, or methane. And the ratio of carbon dioxide and methane release is largely controlled by changes in Arctic hydrology or soil moisture. So you can see in this image that carbon dioxide is produced in dry soils, but methane is more likely to be produced in wet soils. The most important point in this talk is that human emissions control the rate of permafrost carbon emissions. I'm going to show some calculated predictions of carbon emissions from permafrost thaw in this figure. Carbon dioxide emissions from permafrost thaw will be on the x-axis, and methane emissions from permafrost thaw will be on the y-axis. And you can see that on each of these axes, they have corresponding RCPs, so future climate scenarios, that are roughly equivalent to SSPs, that indicate the human response. And they are tied to the range of greenhouse gas emissions that you can see on these axes. The relative impact of methane and carbon dioxide is shown in the pie charts on this graph. And the amount of carbon in petagrams is in the red number there, and that it represents the combined effect of both gases together. And for example, this pie shows a representative Arctic scenario that could be triggered by RCP 4.5. So if you take all the different combinations of methane and carbon dioxide emissions and you pair them with the human emissions pathways, you can see these 9 different scenarios, 9 different worlds of different carbon emissions, which are controlled both by the response of the Arctic system and human emissions. But overall, the level of human carbon emissions sets the path of global warming. And to put these carbon numbers into perspective, this graph on the right shows fossil fuel emissions from countries around the world, with the legend indicating the cumulative emissions to the year 2100 in both future and historical scenarios. And so if you look at the carbon numbers on this graph and you compare them to those on this legend, you can see that Arctic carbon emissions can represent sort of a country of permafrost. It's equivalent to a large country's carbon emissions, but the exact number is going to be set by human action. And no policies are currently dedicated to reducing these numbers directly, but the more we curb emissions by following a lower RCP scenario, the less will be released by the country of permafrost. And again, human emissions directly ultimately control permafrost carbon release, but one way to understand the timing of this release is through carbon dating techniques. And we can measure the age of the carbon that's being respired from the Arctic. This plot shows a time series of carbon release from a tundra site in Alaska, and the x-axis represents the year that the carbon was emitted, and the y-axis represents the age of the carbon that was emitted in that year. And so younger carbon emissions are higher on this plot, and older carbon emissions are lower on this plot. What you can see is that through time, the Arctic is increasingly respiring old carbon as carbon dioxide. And so it's releasing this old carbon that used to be sequestered in the ground, and it's entering the global carbon cycle for the first time in thousands of years. And so these measurements not only show the rate of permafrost thaw and the rate of carbon emissions, but they also emphasize the need for field measurements and more sophisticated monitoring in the Arctic. Thanks. I'll pass it along to you.
Yeah, hello. So I will talk a little bit about the distribution of permafrost, and what you see here on the map is something specific for permafrost, which is different from other parts of the cryosphere. So other parts of the cryosphere, sea ice, glaciers, ice sheets, snow, they are defined by ice and they can be seen at the surface. And permafrost is defined by temperature, so it's different, and it's a subsurface phenomenon. And that's why we need to understand what the ground temperature is doing in these regions. There are global networks called the GTNP, Global Terrestrial Network for Permafrost, which is using boreholes and measurements of the active layer depth in permafrost regions to understand what is permafrost doing actually in these regions. And we try to understand also this type of process, the change of permafrost, by using modeling and remote sensing. Remote sensing is more difficult than other parts of the cryosphere, not at the surface, but we can use certain remote sensing products to drive models, for example, and that was done here in this example from an ESA CCI permafrost project. So what we see here is the ground temperature development modeled for almost 20-year period at 2 meters depth. And what we see is that there's a rise in degrees Celsius per year, actually. And so we see a strong rise in northern Siberia, but also in other regions. And if you look careful here, this is a small animation showing the difference between those 2 years, 1997 to 2019, with these model temperatures, what they mean for permafrost fraction in these areas of the northern high latitudes. And so we see, if you look very careful, that especially at the southern margins of the permafrost extent in Siberia, but also in Canada and Alaska, we see a shrinkage of permafrost in these model results. But we see that also in the field, actually, using borehole data. So, and this is basically in step with the warming Arctic, the rapidly warming Arctic, so with atmospheric drivers. So what does this do with permafrost? Permafrost region disturbances are very important. They are rapid processes, so it's not a gradual thaw necessarily in all of the region, but there's some regions or local places where thaw can happen very quickly. So causes of this can be fires in the tundra or boreal forest regions of permafrost, erosion along rivers, shorelines of lakes and the coast, but also lake change. Infrastructure interacts with permafrost. There will be another breakout session this afternoon on infrastructure and georisks from permafrost thaw, and thaw subsidence. So we saw this picture before. I want to point out again, so there's the seasonal active layer on top of permafrost. And this is a very thin layer that buffers the permafrost that lies underneath from the warming in the atmosphere. So if you think about looking at this picture, for example, in Siberia, very thick ice-rich deposits, which are protected right now from the warming atmosphere by this thin active layer. That's not much protection, actually. So we have many regions, especially in Arctic lowlands, that are endangered, basically vulnerable to Arctic warming. And Gustav already mentioned, so many of these processes are irreversible on human timescales especially, so we're not looking at millennia or multiple millennia, but on very short timescales of several decades, century. And so especially the loss of old thick ground ice, like we see here in the image, is irreversible. The deep thaw subsidence, so the change in topography, is irreversible. With that comes the change in the hydrologic systems, so runoff systems, river systems change, and of course the old carbon. So the old carbon is locked in permafrost in many regions for millennia or even tens of millennia. It's carbon from the last ice age in some regions. So in rapid permafrost thaw can accelerate carbon release. So that's an example from a thaw slump in northeastern Siberia, one of the largest thaw slumps on Earth actually. So you see the scale of these features by looking at the trees. So these are full-scale trees at the top. So this feature is, almost a kilometer across, or more than a kilometer actually by now, and more than 50 meters deep. So it not only taps into surface carbon at the soil surface, but it taps into very deep carbon and very old carbon. So rapid thaw affects about 20% of the permafrost region, but could increase carbon release from the region by 50%. And so some of this deep thaw can reach carbon that was locked away for more than 500,000 years. So very, very old carbon. And so this gradual thaw that we heard about can release up to 200 gigatons of carbon, but this rapid thaw may add another 60 to 100 gigatons of carbon by 2300. And a few more examples on these thaw slumps as one typical feature of rapid thaw. So a few studies show already that the formation of these features is accelerating. So this is an example looking at a large region in North Siberia, 8 million square kilometers. And they found that between 2000 and 2020, there was an increase in the area affected by Thor slumps more than 300%. So a tripling of the amount of Thor slumps area affected, more than 50,000 Thor slumps in that area. Another study from northern Canada, looking at Banks Island, a very large island in the Canadian archipelago, found similar things. The timing is a little bit different, but on the lower graph you see how the cumulative area of Thor slumps on that island like really took off in the 90s, late 90s, and the maps show basically from a few Thor slumps occurring in the mid 80s to thousands of Thor slumps in the 2010s. And the final slide here, we can use satellite monitoring to look at regions in permafrost, in the permafrost domain. So that helps us to look at the processes at the surface, at the thaw processes, where things are changing rapidly. So by now we have nice time series in optical data, in radar data. So they show us like where we find subsidence or where we find lake change, erosion, and so on, or infrastructure increase. So this is an example looking at 20 years of data from Landsat, which is available for the Pan-Arctic by now. And so this is an example from the Russian Arctic, indeed, from the Yamal Peninsula, and we see a lot of lake change, these yellow patches here. So lakes draining, actually, because of permafrost degradation at the surface. We see increased wetting in some areas, these bluish areas. We see new oil and gas infrastructure in this particular case, or a new airport that was built in these reddish colors, and lake erosion around the shorelines of thermokarst, of these permafrost region lakes. So the landscape is very dynamic. So we tended to have a look at the landscape as a stable or static feature, but it's actually really dynamic in most of the permafrost regions. So this is a product that is available as a pilot service, providing these kind of disturbance maps for permafrost regions. It will help communities to understand local risks, but also policymakers and decision makers how to handle these risks maybe. And then it also allows monitoring of regions that are now inaccessible for studies on the ground. Thank you.
All right, thank you, panel. So, permafrost soils store more carbon than we see today in the atmosphere combined with the terrestrial vegetation, including tropical rainforests. With warming and permafrost thaw, this carbon can be mineralized and released to the atmosphere either as carbon dioxide or as methane, a more potent greenhouse gas. The timing and rate of projected CO2 and methane emissions from thawing permafrost requires priority attention from the scientific community. While these emissions have regional source in the permafrost region, they will have global implications. So my questions to some of the panelists. First, I think we can start with Guido. So what do we know about how permafrost is changing? What do we see, and how widespread is this?
So permafrost change is really widespread now. We know that gradual thaw is happening pretty much across the permafrost domain. There are a few areas where permafrost remains stable. Rapid thaw can also happen across the permafrost domain, not just in the southern portion, the warmer portion of permafrost, but also in the high Arctic. So I showed this example of Banks Island, for example, which is the Canadian high Arctic, and permafrost degradation is really rapid there. So thaw slumping, but also ice wedge degradation is happening across the entire region. And that's what we see with borehole data as well. So it's warming everywhere.
Even in regions that should be really cold. Yeah. Great. Anything to add?
No, I think I completely agree that there's multiple lines of evidence showing very clearly that permafrost is thawing and warming very rapidly across.
And there's an acceleration actually, so
Yes.
especially over the last 2 decades that we see.
Thanks. Not nice, but no, good to know. So for Emma and Gustav, what do we know about the timing and rate of CO2 and methane emissions from thawing permafrost?
I think we do know from distinct observational sites there's very good knowledge about how one particular landscape would respond and how it has been responding, and there are continuous measurements of CO2 fluxes and methane fluxes from sites that have experienced warming and permafrost thaw. So I think our system understanding of what happens at the local scale is very good. With that said, the observational network to detect such changes is too sparse, right? So there's a need for a wider observational network. And I think so we just finished a synthesis looking at the greenhouse gas balance of the permafrost region, trying to combine all available evidence. And then we have bottom-up estimates, as we call them, from chambers or flux towers that measure on the ground in a few spots. And then we have satellites that observe the concentration in the atmosphere, and then we have atmospheric measurements that we combine with climate models. And putting that all together, I think what emerges is a quite clear picture of the balances now. We know that the region is basically neutral when it comes to CO2 because some forest is still growing and taking up CO2. We know that it's a net source of methane across the full permafrost region. And we do know that which regions are emitting more methane due to wettening, large extents of wetlands, etc. With that said, the projections going into the future of how this will change are to some extent limited by our knowledge on how much ground ice is vulnerable and how much ground ice will thaw, because we need to know how much ice is there now to project into the future what will become wetter and what will become drier, which will then tell us whether it's going to be mainly CH4 or CO2. I think more observations of ground ice coupled to models is needed.
And just to add to that, I think fluxes are often what we base a lot of our predictions on, but carbon can leave hydrologically through soil as well, which is not entirely captured in flux measurements, so likely these are an underestimate of carbon losses, and carbon can move into rivers and streams.
Yeah, maybe Emma, you could talk a bit more about how measurements of changes in permafrost carbon emissions could be detected, like what sorts of methods, and then what some of the challenges are.
Yeah, so as Gustav just mentioned, we often measure ground flux, so we measure the carbon dioxide coming off the ground surface, either using many different technologies, chamber-based measurements, which capture CO2 being released, or eddy covariance, which can capture a wider footprint of measurements. But again, these don't capture carbon leaving hydrologically. So as Guido mentioned, the landscape's very dynamic and it's changing, especially in terms of hydrology and the different moisture regimes, which can really drive a loss of carbon through soil that's not captured at the surface. And so improving measurements in the field is critical for capturing both of those fluxes. So measuring carbon directly in soil is really important in combination with flux measurements.
Claire, may I make a question for for the whole panel? At this point, you mentioned, I think, Gustav, that there's about 17 million square kilometers of permafrost in the Northern Hemisphere, and about a half of that is in Russia. Could you comment on the fact that the collaboration with the Russian scientific authorities has been very severely hindered in the last 18 months, maybe 2 years? Could you comment on the implications of that for the calculations, the monitoring programs, the observational activity, and also the modeling, which is required to continue examining some of the things that you've been speaking about?
I guess I can start. Yeah, I think, I mean, it's obviously a very large setback for Arctic science. There's no doubt about that. In some cases, Russian colleagues are keeping up the monitoring, or still there are a lot of excellent permafrost scientists in Russia that are, in some cases, keeping up monitoring. It's not given that the data will actually then be able to be quickly exported out of Russia. And I think if we think of CO2 and methane observations networks, I think it is absolutely crucial for the modeling and for the remote sensing platforms, because we do have satellites that can actually remotely sense CO2 or methane in the atmosphere, but without ground data on the ground and in the atmosphere to actually calibrate those measurements, we are not able to sustain high quality observations over long time. So I think we can gap fill to some extent with satellites or with modeling, but that is a little bit like a patch or a band-aid. In longer term, we have to have real ground data as well, because the models and the remote sensing capabilities do rely on quite constant, reality checks against the real observational data. So it's definitely a hindrance.
Yeah, maybe I can add to this. So from the remote sensing perspective, definitely, so we can look at permafrost degradation or permafrost thaw and erosion also in the Russian Arctic, as we do in other regions. And I think that's highly accurate, what we do here. But of course, making the link to carbon mobilization and release is a different matter. So ground measurements for that would be very important, definitely. And there has been a long record of measurements, international measurements actually in Siberia, looking at carbon fluxes. So picking this up sometimes in the future is certainly important to understand the pan-Arctic picture. When that will happen, that's up in the air.
So Gustav, you mentioned in your presentation the terms policy-relevant timescale. Mm-hmm. And you spoke about policy relevance, which I interpreted to mean something like the next 50, 70 years, something like this. In the case of the connection with Russia, what is the policy-relevant timescale?
Of the policy-relevant timescale of geopolitical relations, or of when we need to get the access to data? I'm not sure I followed the question.
Well, you've identified this as a problem, as a critical problem for Arctic science or cryospheric sciences. Is this a problem that we have to work on in the next 6 months so that it can be resolved in 6 years? Or is this a problem that it doesn't really matter for the next 6 years we can carry? It's that the timescale seems to be very different for this problem from the timescale of the carbon release that you've been describing.
I think the timescale of the issue of gaps in monitoring data it's on a shorter timescale than the sort of long-term responses of the permafrost carbon. I think the value of observational times, unbroken observational time series, is very high. And as you mentioned, there are a lot of, actually some of the longest and most high-quality observational time series of CO2 and methane fluxes are from Russia, and those have an immense scientific value to keep them going, or to be able to pick them up again if they have been broken. So I think there's a high scientific value of getting that collaboration working again rapidly.
And I'm just going to finish with one final question again to you, but I think it's an important question that people often don't clearly understand. When we have a long time series, we've collected a lot of data. Could you explain why a data series becomes more valuable the longer it is?
Was that to me?
Yes. Well, because some people say we've collected a lot of data, we don't need to do any more.
Well, I think because most ecosystems or Earth systems are characterized by large spatial and temporal variability, so variability in space and time. And to really be able to understand this variability in space and time, to differentiate what is not perhaps almost stochastic or natural variability, which we would expect in a system even under stable climate, and what is enforced changes coming from us. Those things are really difficult to tease apart. You have a very chaotic system going like this, and then you have a small signal that you're trying to back out of that. And if you have a short time series, you're never going to be able to tell the natural variability of the system apart from the long-term trend that is imposed by, for instance, human climate change.
I would also add that, especially in the Arctic, ecosystems respond differently in the initial stages of warming than they do in later stages. So, for example, in a lot of studies, vegetation starts taking up more carbon initially, and so you can sort of have this offset of carbon release from the tundra, but then after 5 years or so of warming, you see a completely different response.
Good point.
Great. So, on the subject of teasing out natural variability, permafrost, carbon thaw, and effects of other disturbances, last year was a huge fire season in Canada. And these had really strong impacts on both the local communities, but also potentially the permafrost. So this question's to Guido. Could you talk a bit about the role of disturbances, particularly wildfire, and how this would interact and potentially cause a cascade of effects or compound disturbances?
Yeah, that's a very important topic. Looking at wildfires in boreal regions, but also the Arctic regions increasingly. So as we saw in the media also, and people from Canada experienced it themselves, the fire season in Canada was extreme this season. In the years before, the 2 years before, it was extreme in Siberia. So we see an increasing warming in the Arctic that comes with more wildfires, drier ground, drier forests, more fuel for fires. There's more ignition from thunderstorms in the Arctic and the boreal region. So, and these fires have a specific impact on underlying permafrost. So on the one hand, they burn vegetation, of course. That's the immediate emission of the vegetation carbon. But they also burn in the surface soils peat layers. And peat layers are really important for preserving the thermal regime of the ground. So the underlying permafrost is basically insulated or protected by peat. And if parts of this peat is burned away, then this thermal regime changes. And so in more southern regions, in the boreal region, permafrost becomes really vulnerable after fires. So not because the fire directly impacts the permafrost, but it changes the thermal regime. So in the years after the fire, if it was a very intensive fire and lots of peat was burning away, then permafrost starts degrading. And that's what we see in many regions. In some places, permafrost might recover as well, but this will be less and less likely in the future in the warmer Arctic that permafrost can recover after fires. So with increasing fire cycles, fire intensities and fire magnitudes, so we will see increasing permafrost thaw in these regions affected by fires.
Thanks. We also see additional threats to biodiversity and other disturbances, such as insect outbreaks, potentially new species, novel ecosystem combinations. What do we know about how these multiple or compound of disturbance effects might both affect the carbon cycling within these permafrost landscapes and then the permafrost carbon itself? Anybody?
I think in some cases the sort of cascade, if we think of sort of cascading ecosystem type responses, are unfortunately rather poorly known. When it comes to insect outbreak or vegetation disturbances, we do know that affects the carbon cycle. It affects the ability of vegetation to actually, because I mean the carbon cycle is a balance of what the vegetation takes up from the atmosphere and what is then decomposed in the soil. And when you add disturbances on top of that, the vegetation's ability to absorb and keep carbon is just weakened, which means that the carbon the carbon fluxes from the permafrost will just be a more dominant part of the carbon cycle. So this type of sort of cascading ecosystem disturbances often lead to a weaker carbon sink in the living ecosystems and then a stronger net source from that system. But it's obviously rather complex to model all of these combined processes, which means that that ecosystem models need to be fully dynamic and coupled to permafrost models to really capture those effects.
And that doesn't happen.
To some extent it happens, but it is not, for instance, included in the models that was in the last IPCC report. So if we look at the CMIP6 family of models, so the models that basically the projections of IPCC AR6 is based on, only 2 of all of those models had permafrost enabled in the models. That doesn't mean that there aren't models that can do this, but it means that the models that go to IPCC are not the models that can do it.
And this is probably important and something that we should.
Yes,
further work on.
certainly, yeah. I guess that was implicit, but yes, I definitely. And there has been, I want to say, there has been massive improvements in permafrost dynamic modeling in the last decades. There are a lot of models that actually do a very good job, and there are a lot of modeling groups working on this, and there are many model versions that do a very good job with dynamic permafrost processes. It's just that if you want to have an Earth system model, a global climate model that is that is stable all over the Earth, that might not, or that works best everywhere, that might not be the version that works best in the Arctic. Because Earth system models tend to have different versions that are specialized for different regions.
Great. I'm going to
I guess I was just going to add that I think permafrost thaw itself is a disturbance, and so I think that adds to the feedback of this loss of ground ice creating an ecosystem disturbance itself that's altering the carbon cycle. So
Yeah.
outside disturbance is only compounding that.
Good point. All right. Nearly final question. Are there other things or other factors that we need to consider with permafrost thaw that could affect northern communities and wildlife beyond the infrastructure that Guido had mentioned? For example, things that would impact people's health or mercury, anthrax.
I was going to mention mercury. That's emerging as something northern communities have identified as a concern of theirs. And
Could you talk a bit more about it?
yeah, so mercury is deposited naturally across the Earth, but it's accumulated in cold regions, and as it accumulates and then thaws, it becomes it's converted to its toxic form by microbes, which can enter groundwater and cause mercury poisoning.
And yeah, and actually, and mercury binds to carbon. So so the carbon cycle and the mercury cycle is very tightly coupled in the permafrost region. So the processes that release carbon also release mercury, which then can bioaccumulate.
Yeah. It's also not nice.
I know food security is also an issue, so the shifting ecosystems changes the food sources for a lot of communities that rely on subsistence, hunting, fishing, and then food ground storage as well. So, because energy is really expensive in these areas, they use the cold ground to store food, and that's altered by permafrost thaw.
Maybe adding to that in terms of food security or subsistence, so many of the communities in Arctic remote regions rely on freshwater sources for lakes, so lakes around the communities in the vicinity. So if some of these lakes drain, so the community quickly has a big problem finding good freshwater sources. So there are a few examples actually where this happened. So Point Lay, for example, in Alaska, the freshwater lake that the community used drained in 2016, I think, and so they were in need to find another freshwater lake nearby, which is not so easy. It's a coastal village, so some of the lakes have brackish water, and so it's a really important issue for them. So having a freshwater source, and there's also water quality issues associated with thawing permafrost. So there's a lot of material eroding into aquatic systems, so be it lakes or streams or the near coastal environment. Which changes the aquatic ecosystems and the dynamics there. So there's more nutrients there, there's maybe even contaminants, so we talked about mercury, but also other stuff that goes into these waters. And so that's also a concern for the communities locally and the people living in the Arctic, relying on these waters to be clean and usable.
Great. Thank you, panelists. I wanted to give you an opportunity for one last comment before, or final word before we switch to questions from the audience and our recommendations.
Yeah, maybe I start with that. So apart from the carbon cycle, there are of course other biogeochemical cycles that are important. So we heard about mercury, but another important component is, or element that is stored in permafrost and released when it thaws is nitrogen, for example, and it's really tightly coupled to carbon cycle processes. So we start looking into how nitrogen is cycling in permafrost region when it thaws and how that affects also greenhouse gas production. So there's nitrous oxide, a very potent greenhouse gas that can form based on release of nitrogen from permafrost, but it also affects the vegetation and other processes of the carbon cycle in permafrost regions.
I guess I'd go back to the main point of my talk, which is that we have a lot of control over these processes, and the more we work to curb emissions, the fewer unknowns we have with the permafrost carbon cycle, and also the more likely we are to reduce permafrost carbon emissions.
Yeah, I think I'd just like to sum it up with that permafrost carbon science is, I mean, obviously there are a lot of unknowns or uncertainties, but we did definitely know enough that you know, we have a good sense of where we're headed if we don't curb emissions, and I think there's definitely enough knowledge to emphasize the need to act.
That's a great note to end on. So with that, Guido, maybe you could advance us to the next slide. Here.
Sorry.
So these are the recommendations that we have submitted to the organizers and the Scientific Advisory Board for this summit. So to summarize these, we think it's really important to quantify the carbon emissions from thawing permafrost because of the implications for climate warming and the permafrost carbon feedback. Another important area for research would be to quantify the carbon emissions associated with disturbances, including wildfire, coastal erosion, and other topics that we touched on today. A third recommendation would be to involve the local communities that in the locations where we are working, both in the science, but also to make sure that the science addresses the local challenges. So as Guido pointed out, there are people that live in these areas and they have challenges associated with permafrost, so it's important to work together with them, and this needs to be increasingly adapted in our research. Finally, we'd like to recommend continued support for permafrost science, given the remote access and large expenses associated with maintaining these remote sites. But we feel that it's really important to continue to understand and measure and to continue long-term monitoring in order that we can understand how permafrost is changing, how permafrost carbon is changing. So with that, I would like to open the floor for audience questions. Yes, we have a microphone for you.
Thank you very much. I think it's very, very educative. We are from the International Center for Integrated Mountain Development, ECMO. So we have also just started working on permafrost and understanding it. So, you know, we learned a lot from all the panelists here, the presentations and so on. But what is amazing is also the, you know, the geophysical context. Now in the mountains, permafrost has an immediate impact on people's lives and livelihoods, because when permafrost thaws, it leads to failures of whole slopes, no, mountain slopes coming down, land degradation, erosion, all that. So that has got more immediate impact on people's lives and livelihood. And here we would also like to see some language being incorporated there to look at, you know, the beyond carbon, beyond changing hydrological regimes and so on, something on the landslides.
Yeah. So actually, what I didn't say, and I should have said, this is a subset of the recommendations that's addressing permafrost carbon. So the full recommendations do include geohazards, and I'm leaving it to Chris to
That's
So-
the next session. Yeah.
Yes,
discuss in the next
if you
session.
if you come here at
Well, he has a talk.
yeah, but we will have a conversation after lunch in which we will be directly addressing many of the things that you have just described, and there are specific recommendations about that, but that you will see those after lunch.
This is just a very small question. Recently, I saw a TV news. It talked about permafrost saying a carbon bomb. Do you agree with? I just wanted to get your opinion. How could we use that term, carbon bomb?
I don't think it's no. I don't use it myself, and I mean I think even in the most dire projections, permafrost would emit something along perhaps 10 up to 20% of human emissions. So I think permafrost emissions are not going to just be the thing that completely changes the climate pathway. What humans do matters much more. But then, if humans limit their emissions, the permafrost emissions will also be limited. And permafrost release is also gradual. The bigger problem is perhaps that it's so long term that it persists for centuries. So every tenth of a degree matters, but it's not a bomb per se. I don't think so, at least.
But, well, so I would debate a little bit. I would agree with the issues with it long term and the size relative to human emissions, I think. But I think also the magnitude when you compare it to other natural feedbacks is substantial. I mean, you don't really hear about soils in any other area losing or potentially losing anywhere near as much carbon. So this is, I mean, it's perhaps, I would also caution a bit on the bomb, even though I may have used this myself at one point or another. It's not an insignificant source. So I think some gravity and recognition of the magnitude of the source is important.
It's a country.
Yeah.
It's a country, yeah. Okay.
The sleeping giant, yeah, more or less.
I have just one question and also maybe recommendations, because these 4 recommendations are very concrete based on the risk discussion we just had. I'm wondering, like, because we already talk about impacts on ecosystem and probably impacts on biodiversity. So I do not see that explicit recommendation in this one, where there is very, very, very limited research, especially across the world, but also in the Himalayas. So maybe somewhere here, ecosystem and biodiversity would be reflected. That would be really great.
Great.
I should say that we have one recommendation, I can't remember if it's in here or on one of the others, where the ecosystem impact is most directly observed and experienced by communities who depend on wildlife for their food security. And so the connection that we have made, it may not be in these ones, but you would see it this afternoon. The connection we have made is between the adjustments that are occurring that influence the community's food security. Now, the reason that we have done this is because if there is to be action, it must be action which everybody is endorsing, action that we bring everybody along in the same direction. And it's very difficult to engage everybody unless the action is seen to be relevant directly to their own experience. And so the wildlife connection with food security is the one that is the most direct connection for the people who live in that environment. Yep, Tina?
Thank you. And this may also be covered in another session, of course, but you only here touch upon the carbon emissions, but there's also carbon release that maybe will not emit, but will go into the ground or be absorbed in other ways. Would you have that here, or maybe in ecosystems, or? And then also when it comes to emission, I mean, we need to quantify the emissions first, but should we also quantify how much then can be absorbed again by the natural systems?
Yeah, and I think that that is an intricate part of that is first having observations, because when you set up an observation system that quantifies permafrost release, in those same sites you also tend to actually measure vegetation uptake, so that you do monitor the full carbon cycle and the energy balance and all of these things together. But then to really be able to assess that and to project it, we need to have the permafrost dynamics coupled into dynamic ecosystem models. And that is the only way to get all of those balances together, because we need the vegetation responses and we need the dynamic vegetation responses as they will evolve under nutrient limitations and other things which are not yet in the models. So I think when we get the models to the stage where they can actually do permafrost well enough, we sort of get that. We get that from the models, because the models are actually doing vegetation dynamics quite good already. So I think that by getting permafrost processes into the existing land surface models, ecosystem models, we will get the full carbon cycle response, including the sink in the vegetation that partly offsets the release from the permafrost.
I think the challenge here is also disturbances change that system that we hope to understand. Just look at the wildfire season in Canada. The carbon that was burned there in vegetation, that's hundreds of millions of tons of carbon only this season. And so where we previously hoped, well, vegetation will recover some of the carbon that is emitted from permafrost to the atmosphere because the forest line is shifting northwards and there's shrubbification in the Arctic, and this will suck up some of the carbon out of the atmosphere. It looks like increasingly that this may not be true, actually, because we will lose vegetation in these areas that are really drying up in some places.
I can just add to that is that unfortunately what we see is that as models get more advanced, and you actually have, when you have a more advanced vegetation dynamics cycle that also includes, for instance, nitrogen dynamics, we don't see this, because earlier models would actually predict that the vegetation would love it so much it would just be growing and growing and basically offset the permafrost release. But the models that are more realistic don't project that. And the observations don't support that either, because there are so many other things that limit plant growth. It's not just CO2 fertilization making the plants happy, but there are other things limiting it. So the more advanced models don't project this really strong vegetation offset of permafrost release, unfortunately.
All right, let's take a final question from Ugo.
Thanks. I'll make it quick before lunch. This is a question only for Emma and not for the for the other talkers. I think the realization that permafrost has a global impact is fairly new when you look at the history of science. And parallel to that, we are a very small community in terms of science. And the future is that we need more people from a set of different countries to get interested and excited about permafrost, but also to open positions about that. What is your feeling at your stage in your career about the current situation and those needs?
That's a great question. I'm excited to be here as a representative of the Permafrost Young Researchers Network, which is growing actively. So that's a good sign for the future of permafrost research. But I think the reason that I'm in this field is to help solve climate change and to understand a really important feedback in the global climate system. And so it's really exciting to be here and to finally be speaking to policymakers who I hear so much about and I learned how to communicate with them. And so I think encouraging early career involvement in events like these is really helpful for creating a space for early career researchers to get them excited about science and to keep them involved in the reason that science matters.